This conference will now be recorded.
All right, everybody. Hope you're doing well. I know this is a challenging time across the Weather Service. It's great to hear everybody staying well. I'm Jordan Girth with the National Weather Service Office of Observations, the Leveraged Observations Lead. We're starting something new. Some of you may have heard about the Polar Book Club, and that was an opportunity to really work with the field to encourage the use of satellite data to improve the forecast process. We're expanding that into satellites now to include GOES. So what we're going to do with this form, and we're going to be looking for your feedback, is to really bring in forecasters, people at the field level that have used some of this data in operations, and hope that we can expand the use across the Weather Service to multiple offices. So this is a great opportunity to share ideas across the field. How this will work is, first of all, this is being recorded. The Q&A will be after the presentation. The presentation only lasts about 15 minutes. We understand your time is valuable. And if you're interested in being a future presenter, please let us know. We will be sending around a feedback survey if you have ideas for how we can improve this. The Tower S team on the call today, we have David Blutis and Lee Byerly, who have really been instrumental in putting this together. They're available to help you with data access and AWIPS configuration needs. So please always feel free to reach out to the Tower S team if you have any questions about where satellite data is in AWIPS, or if there's a new product, how you can receive it or configure your AWIPS. And also we have members of the training team on the call today. I see Brian Mata, perhaps Ross Van Til, members of our cooperative institutes. They're also available for creating training materials, or if there's something you're uncertain about, please feel free to reach out to the Forecast Decision Training Division, because I think that they have a number of different resources that may be able to assist you. So I appreciate it, everybody joining us today. Without further ado, I'd like to introduce Michael Stroz, who's been a forecaster in the Weather Service since 2008, and he's gone from coast to coast, from Eureka to Charleston, South Carolina, and he's had a lot of experience in marine issues, leading the, or he's at least been a member of the Office Marine team, latest rip current science, improvement to the Nearshore Wave Prediction System, and working on decision support services. So with that, I'll turn it over to you, Michael. Thank you for being our first presenter in the Satellite Book Club.
Okay, thank you very much. Can everyone hear me relatively clearly?
Yep, you're perfectly clear.
Okay, very, very nice. Everyone, thank you for joining us today, especially given how difficult times have been. I also echo a lot of what's been said, that we all are going through difficult times and trying our best to stay healthy. With that, basically, as already said, I'm Michael Stroz with the National Weather Service in Charleston, South Carolina, and today I was asked to go and speak briefly about how we use scatterometer wind data in marine forecasting here in our local weather forecast office. So one thing I would like to start out with, which a lot of people, especially those in landlocked WFOs and even those that do a lot of non-marine type of forecasting, the density of observations varies greatly from the land to the ocean. But most people just don't realize just how great the differences are between land observations and marine observations. So I'll go and show an example here. Looking across the New York City metro area, so you can see the tri-state area right there right now. And pretty much I went and put all the METARs on the map that I could load through AWIPS. Now there's certainly more than just METARs. You have RAWs and various other data sensors, but just for simplicity purposes, I went and put the METARs on the map. And you can see quite a good bit of coverage within the New York City metro area. However, you go and compare that with another location, and you can only see pretty much 1, 2, 3 locations, pretty much very little data across this remote area. And this happens to be an area just north of Las Vegas. So down where the arrow is, Las Vegas metro area. North of that, you're 1, 2, 3 points, and pretty much desert areas, not much data there. But what's a little bit interesting is when I went and compared these two, they're actually the same size as far as aerial coverage goes. If I had a little mileage marker on the bottom, they would both be showing the same amount of size. So, but take my word for it, they're both the same area coverage, and you can see the vast differences in the amount of METARs and land observations from the New York Metro to north of Las Vegas. And I mean, even some other things that catch my mind, it's like you have one county that's pretty much larger than the state of Connecticut. So just vast differences in the amount of land and observation coverage between a metro area and a remote area. So when we go and keep that in the back of our minds, you have to go and start looking at the marine environment. Now, our marine environment, it covers pretty much the waters of southeast South Carolina and southeast Georgia. So it's a big view. I'll go and zoom in now a little bit closer. As far as our marine responsibilities go, we have the Charleston Harbor as a marine zone. Then we have pretty much 4 zones that go and cover the South Carolina waters 0 to 20 nautical miles, 20 to 40. So 4 zones in total. And then we have 2 zones for the Georgia waters, 0 to 20 and then 20 to 60. Now, they seem straightforward, but they're not, because when you start looking at the responsibilities that we have, it kind of varies. In red, I had the short fuse warning responsibilities that we have to do, and that's would be for special marine warnings, marine weather statements, and we're pretty much having to do that for the harbor, along with all the South Carolina waters from 0 to 40 nautical miles, and then the Georgia waters from 0 to 60. But then you look at the forecast responsibilities for the CWF, the Coastal Waters Forecast, the NWW, the marine weather warnings, and they're a little bit different. We only have to do those for the harbor, the South Carolina waters from 0 to 20 nautical miles, only those, but then the Georgia waters for 0 to 20 and 20 to 60. So you can see a little bit of differences as far as what type of progress we have to do across different zones. And in some zones, essentially, we're kind of competing a little bit with OPC. So that can make things both short fuse warnings difficult based on the zones that we have, along with the lack of data, which we'll go and we'll take a look here. Just again, looking at the METAR observations that we have over our land areas. Decent coverage. I mean, we always want more, but I mean, just something's better than nothing. And how does that compare with the buoys that we have? Well, we have pretty much 4 that we can go by. We have the Edisto buoy 41004, which is southeast of the Charleston, provides the wind and sea data. We have another NOAA buoy that's called Gray's Reef. It's southeast of Savannah, Georgia, and it provides wind and sea data. We have CORMP buoys, which are Coastal Ocean Research and Monitoring Program buoys. One that's just east-northeast of Charleston, and then another one that's Nearshore, which is a little bit northeast of Savannah. And you can kind of see these 1, 2, 3, 4 points here. We also use ship reports that we could get from pilot boats off of the Charleston and Savannah harbors when we're able to get them. So not a great amount of data when you go and you look at it from the ocean side, and especially more when you kind of consider that, hey, some of these areas we're forecasting for don't only have like one wave buoy, like the Georgia waters. That's our only zone in which we're doing a coastal waters forecast that has a wind and seas buoy. The buoy off of Edisto, that's not in our waters technically as far as the coastal waters forecast. That's only for warning responsibility. So kind of when you go and think of that, it's quite a difference as far as coverage and observations and what we do with it. And of course, I mean, once you go and you zoom into the land areas and you start looking at sites right along the coast, you start to get a little bit better coverage. Just looking at quickly some weather flow stations. See the Charleston Harbor highlighted. Then off the coast is the one CORNP buoy, the NOAA buoys further offshore. Closer to Savannah, you can see some more data. But I mean, again, these are observations along the coast over land areas, and mariners are just not on land. I mean, if they're on land, it's pretty much they're getting the boats from on the back of their vehicles into the water, or they're kind of inland just going shopping, bars, or who knows. But pretty much their focus is what's going on in the marine environment. And we have limited data that we can look at. So brings up the question, with the limited buoy data and ship data, how can forecasters fill in some of these data voids? And quite simply, it's using satellite data. The Advanced Scatterometer, or ASCAT instrument, aboard the various Metop satellites, it's pretty much the most commonly used by forecasters for marine winds across the National Weather Service. But we here in Charleston over the past few months had the opportunity to go and test data from the Scatterometer Satellite, known as SCATSAT. And this has been very, very helpful for us because it essentially went and doubled the amount of scatterometer data that we had available. Now, just go and quickly talk about SCATSAT 1. This is information that's already out there, but for those that are not aware of it, it's short for Scatterometer Satellite 1. It's a satellite that's owned and operated by an Indian research organization, launched in September 2016, considered a mini satellite when compared to, say, like the large GOES-R satellites and some of the other big satellites that get sent into an orbit. And pretty much when it goes, its orbital path has it passing overhead roughly from 9 to 10 a.m. and p.m. local time. That's when it's taken the images, but those images arrive in AWIPS at a later time. As far as what's within the wind product itself, the product resolution is 12.5 kilometers. We get 3 pieces of information with the product. It's the wind speed, the wind direction, yes or no if it's raining, aka rain contamination, and the wind speeds are accurate to within 4 knots. But it does have some limitations as well. This product that we get into AWIPS, latency is anywhere from 60 to 180 minutes. As is expected with scatterometer data, it can have erroneously high values in rain. And like with any polar orbiting satellite, you only get about 2 images per day over the CONUS waters. And one flaw with the satellite is it does not detect winds higher than 97 knots, but we're just in general hoping that we never get winds that strong off our coastline. So I'll just go and do a quick showing of the ASCAT scatterometer wind swath with, you can see it has the 2 different swath areas that most of the forecasters use. That's about 500 kilometers wide. And when you compare that to SCATSAT, it's 1,800 kilometers wide. So kind of going back and forth, you can definitely see quite a bit of difference in the aerial coverage between the 2 satellites. And that's definitely helping us forecasters out quite a bit. So with all the scatterometer data, we're able to go and utilize it for our coastal waters forecast. So here I have one example in which we have a SCATSAT pass over our entire waters, and pretty much, not sure how great it shows up on your screen, but a lot of these winds are pretty much in the 20 to almost 25 knot range in green. And then there's a few areas of little bit of white, and they're kind of 25 knot sustained wind barbs. And that's important to note because when you're looking at winds about 20 or so knots, then you could potentially have gusts about 25 knots, which for us, 25 knots is small craft advisory criteria. So when you go and look at this, just from a satellite perspective, it starts bringing up the question, hey, there could potentially be small craft advisory wind gusts going on in portions of the waters. And that is not always going to be picked up based on at the 4 little circles that I have on the map, which go and show where our 4 wind sensor buoy observations would say. So in this case, we were able to go and and use the 20 to 25 knots worth of winds to go and decide for small craft advisories and keeping that up along portions of the coastline. I'll go and use another example that we have for ASCAT. Now, it passed over most of our waters, but what's interesting to note here is we can see this wind divergence, wind speed change across the waters here. So we got north of it, kind of like across our parts of our South Carolina waters, you have kind of a south to southeast wind flow, and then it kind of transitions as one keeps on going further south to more of a light northeast type of flow. But when you kind of go and look at where the buoys are, I mean, you're not really going to go and get a very good grasp of this whole change in wind direction as you can by looking at the ASCAT observations. So in this case, it's a good way of showing that, hey, at this time period, there's definitely a wind direction change, a little bit of the boundary there, and kind of for us to be aware of it for forecasting purposes. And especially once you get to summertime, you have to be more aware of these boundaries for possible convection along the Gulf Stream further offshore for storms to fire off there, or if the boundaries move inland for the sea breeze, you have sea breeze thunderstorms that start. So this is a way that we're able to see various wind changes using ASCAT that we're not able to pick up very well with just a few buoy observations. And we also have the ability to go and combine ASCAT and SCATSAT observations together. So by, in this case, I mean, they're both green, so you can't really tell which satellite is which, but it still gives you the fact that they're both there and showing about the same wind speed that's relatively in good agreement. Now, in this case, the ASCAT data passed over our area at 15Z, and the SCATSAT data was at 1333Z. So about a roughly 90-minute difference, but it means the fact that they're both within, showing roughly the same amount of wind speeds, roughly 15 to 20 knots, shows that they're in good agreement. We can trust the buoys on the ground, matching them up to help go and have higher confidence in the forecast. And when you get these satellite passes that are, say, 90 minutes apart, if you have a transition like front going through, you can be able to monitor those fronts going through a little bit better with the ASCAT and SCATSAT as opposed to just going by buoy observations alone. And I'll also go and show a little bit of a larger image that I was able to grab the other night as well. This is just kind of luck of the draw where these two larger areas here were 3 hours worth of SCATSAT data, and what here would have been a little bit of a hole in the SCATSAT data happened to just by dumb luck get filled in by the ASCAT data, and then kind of south of Florida, and then you can see them both doubling up over the western half of the Gulf of Mexico, and then you even have data like further north into the Great Lakes. So just being able to get both of these satellites together and combine them into a composite definitely helps things out for forecasting and especially for the national centers, but then especially for us as the local WFOs in order to get a bigger scale of things. So kind of wrapping things down, so the pros that we've seen with a lot of the scatterometer data, first and foremost, is just more data to begin with, especially over areas with no observations. That's definitely helpful with the forecasting. It's able to help us verify and make changes to the forecast in near real time as far as do we need to put watches, warnings, and advisories out for small craft, gale warnings, storm warnings, or even worse. And that being able to see that with scatterometer data combined with the buoy and boat observations can help to give us higher confidence in our decision making. It also gives us the ability to see areas where swell is generated further offshore, which may or may not be detected by buoys before it reaches our area. So if you have a remote area offshore that there's no buoys and you see a strong area of winds, possibly gale force or stronger, being detected by scatterometer data, you have to at least be aware that, hey, could that generate some swell that can be heading towards our waters? If so, that's something that we should be aware of for possibly rip currents in maybe the next day or two, depending on the location of the strong winds offshore. And last but not least, the tropical monitoring for both the Hurricane Center, OBC, and then even our purposes. But with every pro, there's some cons, and first and biggest one amongst forecasters pretty much across the Weather Service is latency, latency, latency. The way I look at it is we forecasters have been spoiled by GOES data. We can get 30 seconds GOES data roughly 2 to 3 minutes after it's taken. We can get GLM data from GOES for every minute that it's taken, and we get that into our AWIP systems roughly 2 to 3 minutes after it's taken. So I mean, we're so used to now getting near real-time data from GOES that we're spoiled, and when we get 1, 2, 3 hours of latency from these polar orbiting satellites, it makes it very hard to use and hard to swallow sometimes. And the best example I can use for those that aren't used to it is just imagine that you're using your cell phone at home to look at the radar data, but that radar data is 1 to 3 hours old. You quickly see that it's useful, but not as useful as you would like it to be if it were, say, 5 minutes old. Number 2 is scatterometer product timestamps versus observation times. Sometimes you can have a product timestamp that could say like 2Z, but the observation times could be an hour or an hour and a half before that. And that can lead to confusion amongst the forecasters of, hey, when is the image taken versus what is the product timestamp? So that's something that forecasters need to be aware of, because it's a very easy mistake to make and think you have the right time when you don't. Number 3, SCATSAT product does not update automatically in AWIPS. It's a pretty major issue just because you have to manually update it to get new data. But regardless, it will be fixed in a future build. Number 4, ASCAT and SCATSAT passes are relatively close in time, which is good because you can see transitions roughly 90 or so minutes apart, depending on when the data comes into the system. But it'd be much better if you had them every 6 hours, so you can see transitions roughly with very synoptic times, or if you had more scatterometer data to see new data every hour or something. But that's, in a sense, wishful thinking, which kind of gets us to number 5, the red tape of getting a lot of this data into our AWIP system. We know that there's various red tape as far as things that we have to do to follow procedures and get things done, but then there's other unknowns that pop up that slow us down along the way. So, I mean, but don't take it all wrong. It's like, overall, it's great data to have. It's something that I and a lot of the other forecasters really appreciate it. But there's some flaws to it that forecasters and others need to be aware of. And when those flaws are at least fixed or at least improved upon, then, I mean, you can look at a lot of the polar orbiting data being a very useful companion to the GOES-R and GOES-S and all future GOES data that we're going to be looking at over the upcoming decades. So with that, I am pretty much complete here, and I'll open it up for our questions and discussion.
Thank you, Michael. That was terrific. At this time, we will now open the floor for anyone to ask Michael a question. Feel free to unmute your device if you prefer to do that, or you could ask your question in the chat room there, and we could field your question then. So does anyone have any questions?
Michael, this is Jordan again. Thanks for your presentation. One of the things that we're always interested in when we look for new observation is where there's still gaps. And talking to a lot of marine offices, the shoreline interface is typically where you have a lot of people and a lot of impacts. I understand there's broader responsibilities for a small craft further out, but what are the other challenges that you have, for example, around Charleston Harbor, with understanding what the wind and wave conditions are in those areas of the shoreline that aren't covered by satellite or buoy?
I would have to say it would be the sea breeze, especially now that we're coming into the summer or the summer months where we have a lot of convection. Pretty much we know that the sea breeze is going to form right around the harbor and start moving inland. But I mean, we could see that with radar and satellite, and that's good during the daytime. At night, it pretty much goes and becomes more of a land breeze. And when that goes and moves over the marine environment, that's where we tend to lose track of it and not really get a good feel of it. So trying to get a good sense of how where that sea breeze and land breeze is from the day to nighttime period and potential impacts could have to mariners, along with thunderstorms that tend to fire off of it and potentially could be really, really hazardous or worst case scenario deadly to mariners. Trying to go and follow that is very challenging, and we can do the best that we can as far as buoy obs and ship obs, but being able to have more satellite data in order to try to track that stuff really close to the land-sea interface would definitely help us and all the other offices along the coast out quite a bit.
Thanks.
Michael, we do have a question from Brian Gockel here. He asks, how far out offshore would you like to see the data? Not asking your opinion on OPC's needs, but typical coastal WFO.
I mean, for us, we're kind of one of those, we're typical scientists. If you give us the data or give us the chance to get it, we'll use it. More than likely, for us, we would certainly be happy with anything in the Atlantic or in the Gulf, but knowing that there are various restrictions as far or latency and type of things that can slow the system down. At minimum, we just want the stuff over our waters, but preferably we want it pretty much over the entire Atlantic Ocean, just to pretty much see what's coming, especially when you get calls like, say, from the media, hey, what's going on with tropical storm X, and at least we'll have that scatterometer data that we can look at along with the hurricane center, which can help us out as well. So more data in this case is better, especially considering the size of the ocean.
Okay, terrific. Are there any other questions? We have a question here. One of the cons you mentioned for SCATSAT, what did you mean by timestamp and observation timestamp difference?
Well, what happens is the way that the SCATSAT product is set up is it's an accumulation of the past 3 hours of data. And so you can essentially have, when the satellite goes overhead at, say, 0Z, it may not show up into the product until probably closer to 3Z. And that's quite a bit of a time difference as far as when you have the image or the satellite going overhead at 0Z, but then the image time within the product is 3Z. So it's just pretty much the limits of what we have within the test of the system. It'd be nicer to have it where it would be able to come in every, say, 10, 20, 30 minutes, and you'd be able to see that in as close to real time as possible. But again, with latency and various restrictions and things along those lines and red tape are kind of a little bit limited there. But does that answer your question?
Yes, thank you.
Okay.
Okay, any other questions? Okay, Jordan, I will turn it back over to you then.
Okay, thank you, David. And once again, thank you, Michael, for that. Really appreciate everybody tuning in today. We'll have another presenter lined up for next week, Jarrell Torres, who is the JPSS satellite liaison with CIRA at Colorado State. And he's going to be talking about the JPSS fire monitoring capabilities and the application of the VIIRS Fire RGB imagery. There'll be more information coming in an email from the TowerS team. I'd just like to remind everybody once again that we're very interested in bringing in presenters and hearing from members of the field on topics of interest. So please let us know who you'd like to hear from, or if you'd like to present, or that would be absolutely fantastic. We will have a recording posted. We realize with shift work you might not always be able to attend, so we hope to have this posted perhaps through a YouTube channel, or at least something through the VLab. We'd like to thank Brian Mata and again the Forecast Decision Training Division for all of their assistance with getting this GoToMeeting set up. I think the format worked very well. And once again, just appreciate our presenter Michael and our Tower S team here, David Blutis and Lee Byerly, who are standing by if you have any questions about how to use this data or get it into your AWEBs. With that, I will conclude and thank everybody for their time. Hope everybody stays well, and we'll talk again next week. Bye now.